Hello, everybody, and welcome to the second lecture of week 3. So this is going to be on inverses and the Chinese remainder theorem. So I want to start by recalling a rough definition that we already stated in class today, but let me state it again. So when I say a number system, I'm just trying to highlight, not erase. When I say a number system, that means a place where we can add, subtract, and multiply, subject to the usual rules of arithmetic. So the usual rules of arithmetic, well, addition and multiplication should be both commutative and associative. There should be a distributive law for the interaction of multiplication and addition. There should be special numbers 1 and 0, such that 1 times x is equal to x, and x plus 0 is equal to x. And then anything you can deduce from these rules should also be true. Okay, and I just want to point out, I have a little asterisks here. Starting next week, we'll call such an object a commutative ring, and we'll make maybe a little bit more precise of the definition. But for now, we're just going to work with specific examples anyway. So I just want a way to tie them all together conceptually. And so we'll call that a number system. Okay, so the main examples, and again, we discussed these in class today, are the integers, the rational numbers, the real numbers, the complex numbers, and then the integers modulo n, so z mod nz. Okay, so an important warning, and we saw this a little bit in class, but bears repeating, you cannot always divide by a non-zero element in sort of an arbitrary number system. So I work in the rational numbers or the real numbers or the complex numbers. It is true that you can divide by, if we're in rational numbers, real numbers, or complex numbers, and you sort of take any non-zero element in there, you can always divide by it. So we know how to divide in these number systems. But it's not true that you can divide by an arbitrary element in the integers. So for example, if I try to divide by 2, like 1 over 2 is not an integer anymore. So you can still sort of divide in integers, but like when you do division by, like when you try to divide by 2, sometimes you leave and you end up in the rational numbers. So when I say you can't divide in integers, I mean you can't sort of divide by any non-zero element and necessarily stay in the integers. Okay, and so the same will end up being true sometimes in z mod nz. So sometimes you'll be able to divide by any non-zero element in z mod nz, and sometimes you won't be. And actually, I claim we more or less saw in class today when this will be the case. So what does it mean to divide? Well, okay, so when I'm dividing, I should be able to sort of do x over y. But really, I can think of that instead as being x times 1 over y. And then the question is, what is 1 over y? Well, here's a definition. 1 over y is just any number such that y times 1 over y is equal to 1. So it turns out, so this pins it down if it exists, but such a number may not exist. So if it does, then we say it's a multiplicative inverse of y. And then we can use it to divide by y just using this equation. So interpreting x over y as x times 1 over y. And so if you think about it, you'll see that's going to sort of satisfy all the things we expect division to satisfy. Good. So the real question then is like, which elements have multiplicative inverses? We saw some examples in class today. Let me recall the first couple. So in the rational numbers, real numbers, and complex numbers, well, you can always compute 1 over y as long as y is not 0. So any number, any non-zero number in these settings, in these number systems has a multiplicative inverse. But in z, so in the integers, the only things that have multiplicative inverses in z itself, so that the multiplicative inverses are also integers, are y equals 1 and y equals minus 1. Because 1 times 1 is equal to 1, and minus 1 times minus 1 is equal to 1. So here sort of minus 1 is its own multiplicative inverse, and 1 is its own multiplicative inverse. So if you take, on the other hand, you take 2, well, you can sort of form 1/2, but that's not an integer. So this has 2 has a multiplicative inverse in the rational numbers, but not in the integers. So, and then you guys spent a lot of time in class today looking at the following sort of question, like when in Z mod NZ do you have multiplicative inverses? And so just as a concrete example, if I look at Z mod 15Z, then I have the equation 2 times 8 is equal to 1. So recall that's because 2 times 8 is 16, and then sort of to work in Z mod 15Z, you sort of shift by a multiple of 15 until you're between 0 and 16. So between 0 and 15. So sort of we shift down by 15 and we end up at 1. So 2 times 8 is equal to 1 in Z mod 15Z. And so is 8 times 2. I mean, 2 times 8 is equal to 8 times 2. So that means 8 is the multiplicative inverse of 2, and 2 is the multiplicative inverse of 8. So these are multiplicative inverses of each other. So these in particular 2 and 8 both have multiplicative inverses. If I look at the number 3, it doesn't. So let's wrote out all the multiples of 3 in Z mod 15Z. So here I'm going to look at 3 times x, where x goes from 0, 1, 2, 3, 4, 5, all the way up to 14. So I'm sort of looking at all of the elements of Z mod 15Z. I'm looking at 3 times that element, and I get 0, 3, 6, 9, 12, 0, 3, 6, 9, 12, 0, 3, 6, 9, 12. I mean, good exercise to think about why that repeated like that. But in particular, I never got 1. So there's no element in Z mod 15Z that when I multiply it by 3, I get 1. So that means sort of there is no 1/3 in Z mod 15Z. There's no 1 over 3. So 3 does not have a multiplicative inverse. Should write that. This is never 1, so 3. So 3 does not have a multiplicative inverse. In Z mod 15Z. Okay. So, right, so in class you were investigating, so you wrote down all these times tables, and then you were investigating which elements in Z mod NZ are going to have multiplicative inverses. And let me recall sort of a restatement of that problem. This is how it's written on your worksheet. So the question of whether an element in Z mod NZ has a multiplicative inverse, that's the same as saying, okay, so if I have an element in A in Z mod NZ, then this is going to have a multiplicative inverse if and only if I think of A as just being an integer, then there's some other integer B such that AB is congruent to 1 mod N. So in that case, the multiplicative inverse is sort of, well, it's B, but it's, and here I just said any integer, so B could be really big, so it's the unique integer, so the unique number between 0 and n minus 1, such that K is congruent to B mod N. So because we sort of define Z mod NZ to just be the collection of number, like the symbols 0 through n minus 1, with multiplication defined sort of by doing regular multiplication, or but then taking sort of the remainder when you divide by n. So I mean, sort of this B is giving you the right thing, but you just have to shift till you sort of land between 0 and n. So you do this. Okay. Good. But so this is a restatement of when you're going to have a multiplicative A as an element A will have a multiplicative inverse in Z mod NZ. And okay, then once we've restated like this, we can write down a simple criterion. So this is something that some of you will have already observed in class when we were working through these timetables. So the statement is, if I have a number A and an integers A and N, and so I'm going to look at mod N, and I'm looking for sort of a multiplicative inverse of A. So the statement is that there is an X, there's another integer X, such that A times X is congruent to 1 mod N, if and only if the GCD of A and N is 1. Okay, so let's go ahead and prove that. So first, let's suppose that AB is congruent to 1 mod N. Well, this means, sorry, not AB, A times X. So suppose there is such an X. Well, if I unpack what AX congruent to 1 mod N means, we can rewrite this as ax is equal to 1 plus some multiple of n, which I'm going to write as n times y for some n and z, or for some y and z. Okay, and then I move it to the other side, so I get ax plus minus n times y is equal to 1. Okay, and so, but now we're done, because what you'll observe previously is we can only get like, and this is the GCD equation, right? So anytime we can sort of write down a linear combination of x and y with integer coefficients, we're always going to get a multiple of GCD. So the right-hand side has to be a multiple of the GCD of a and minus n. So I'm sort of, I should have written this slightly differently. Sorry. I should have written this n times minus y. Get sort of in the form we're used to. So this is supposed to be the GCD of a and n. So, and if you're getting 1 over there, then that means that GCD has to be 1. Okay, good. So that proves one direction. That proves that if there is a solution to this equation, so if you can find an x such that ax is congruent to 1 mod n, then the GCD has to be equal to 1. Let's talk about the other direction. Well, and you basically unpack it the same way. So if the GCD is 1, then sort of we know that we can find, so we know by the fundamental theorem of arithmetic, as we called it, and as it's called in the textbook, we can find x and y and z such that ax plus ny is equal to 1. So ax, so that's the fundamental theorem of arithmetic that applies this. We can find x and y, z such that ax plus ny is equal to 1. And that 1 is just because that's the GCD. So ax is equal to 1 minus ny, which is congruent to 1 mod n, because I just took 1 and I subtracted off some multiple. So ax is congruent to 1 mod n. Good, and that's what I was looking for. So I was starting from having the GCD of a and n be equal to 1 and going to saying that I can find a solution to ax is congruent to 1 mod n. Okay, so good. Another thing we learn when we do this is an algorithm for finding the inverse, because, okay, we saw like when we write ax plus ny is equal to 1, then sort of x is going to give you the thing that sort of encodes the multiplicative inverse. So and now to get the multiplicative inverse of x, of a and z mod nz, you just sort of shift x by a multiple of n until you're between 0 and n. So, but we know how to find such a solution. We know we can find a solution to ax plus ny equals 1 by unfolding the Euclidean algorithm. So the Euclidean algorithm computes the GCD, and then we saw how you sort of unfold it back in order to get a solution to this kind of GCD equation. Okay, so just an example, you can use this to solve equations in Z mod NZ. Maybe self some more space. So say I want to solve the equation 17x is equal to 5 in Z mod 50Z. Well, what's the idea? I want to sort of, well, how would I solve this like in the rational numbers? I would just multiply both sides by 1/17. So I would sort of get rid of the 17 in front by multiplying by 1/17. So the idea is sort of multiply by 1/17 which is that means I should multiply both sides by multiplicative inverse of 17. Okay, well, if you do it in your head, you'll see that 3 times 17 is 51, which is 1 mod 50. So such an element is given by 3. So the multiplicative inverse of 17 in z mod 50z is 3. Okay, so if I take 3 times 17x equals 3 times 5, well, now I get 51x, which is just x. So this should be a congruence. Oh, sorry. Right this way. Z mod 50z. So I get 3 times 17, that's 51, which again, mod 50 is 1. So I get x is equal to 3 times 35, which so I can multiply it. I get 105 when I multiply as integers, but then I have to take the remainder when I divide by 50. So I get 5 in z mod 50z. So my solution is x equals 5. And I can go back and check that out. If I do 17, times whoops. Okay, this is a good example of how you can do everything wrong. I did that wrong. So this is why you check your answers, right? So, and when I multiplied that out, I did 17 times 5 is 85, which is not congruent to 5. Like it's not equal to 5 in z mod 50z. The problem is I'd written 35 here instead of 3 times 5. So I wasn't very careful about my multiplication. So let's try this again. So now I get x is equal to 15. Okay, and you can now multiply this out. You get 17 times 15 is 205, which when I subtract off a multiple of 50 to get between 0 and 50, that gives me 5. So that really is a solution of this equation. Sorry about that mistake I made. Okay, great. So using inverses, you can find a solution. Here, I just happened to look at this and know that 3 was a multiplicative inverse. I just got lucky and said, okay, 3 times 17, that's 51. So 3 is multiplicative inverse. In general, the first step in solving a problem like this would be you'd use this unfolding of the Euclidean algorithm to find the multiplicative inverse of 17. And then once you knew that, then you'd multiply both sides of the equations to solve it. So you have a few problems on your worksheet, and one of the required problems has you work through some examples like this. Okay, so next topic, closely related to this, is solving a different type of equation using congruences. So let me take 2 integers m and n. Let me look at some element a in z mod mz and some element b in z mod mz. And I want to ask the question, can I find some other integer x such that x is congruent to a mod m and x is congruent to b mod n? So I'm picking 2 integers that I want to know what x is modulo that integer. And then I'm looking for the integers x that satisfy both those conditions. Okay, so an example, I could ask, is there an x in z such that x is congruent to 1 mod 2 and x is congruent to 2 mod 3? So the answer is yes. You take x equals 5. So x is odd, 5 is odd. So 5 is congruent to 1 mod 2. And then so let me write this. I answer this is 1 plus 2 times 2. So it's congruent to 1 mod 2, but it's also equal to 2 plus 3. So it's congruent to 2 mod 3. Okay, so it's satisfied. So this is an x that satisfies both of these. There are more solutions. X equals 11 also satisfies this, because somehow 11 is equal to 5 plus 6. So if I add 6, that doesn't change me mod 2 because 6 is 0 mod 2. And it doesn't change what happens mod 3 because 6 is 0 mod 3. So this is going to 5 mod 2 and to 5 mod 3. So adding the 6 didn't change it. And you could add any multiple of 6 and you would still get a solution. So actually, if you want to sort of enumerate all of the solutions, you just find one of them, start with 5, and then add any multiple of 6. And that will give you another solution that really will give you all of them. Okay. Let's do another example. Can we find something that's congruent to 0 mod 2 and 5 mod 6? So, okay, this one I don't see immediately. So let's just start writing out the possibilities. So we could have x equals 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and so on. And then I'll just write down x mod 2, and I'll write down x mod 6, and I'll just sort of see if I get a solution. So if we have, well, if x is 0, then it's 0 mod 2 and 0 mod 6. If it's 1, it's 1 mod 2 and 1 mod 6. If it's 2, it's 2. Okay, so this first one is mod 2, so it's just alternating where it's even mods. Let me fill out this first row. So we get 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, and so on. And this row, mod 6, is going 0, 1, 2, 3, 4, 5. And I had 6, so I'm at 0, 1, 2, 3, 4, 5. 0, 1, so on. Okay. And let's see how we did. We're looking for one where sort of we have a 0 in the first row, the 5 in the second row. It's probably easier to look for the 5s in the second row first. So when we have a 5 down here, we have a 1 up here. And then next time we have a 5 down here, we have a 1 up here. And those are the only two places we have a 5. So we haven't found a solution yet. But actually, that means we've gone far enough that we're never going to find a solution. Because if you think about it, sort of I'm looking at something mod 2 and I'm looking at something mod 6, then sort of if I change x by a multiple of 12, that's not going to change x mod 2 and it's not going to change x mod 6. So somehow every 12 things, this pattern is just going to repeat on both sides. Good, but in fact, a little bit more. So somehow there is no solution to this congruence. But in fact, a little bit more is true. It's not just true that this repeats every 12 steps, this repeats every 6 steps. And the reason is sort of 6 is 0 mod 6, but 6 is also 0 mod 2. So I got 12 just by multiplying 2 and 6, but actually sort of, I don't need to multiply 2 and 6, I just need to take their least common multiple to get something that's sort of 0 mod both of them. Right, so okay, so if I change x by 6, I'm not going to change what it is mod 2, and I'm not going to change what it is mod 6. Okay, so I actually only have to look in this first 6 entries. So I'm going to look here, and here I see there's no solution, so I'm done. I mean, you can sort of think about it abstractly. So why was there no solution? Like say I wanted to write down a justification. Well, you could sort of write down some version of what I just said, or you could just observe. So if x is congruent to 5 mod 6, then x is equal to 5 plus 6 times n, or 6 times q, let's say, for some q. But then, well, that's always going to be an odd number, right? Because 6 is divisible by 2, so this is just congruent to 5 mod 2, which is congruent to 1 mod 2. So, I mean, if I'm congruent to 1 mod 2, I'm not congruent to 0 mod 2. So somehow, the problem here is created by the fact that 2 and 6 share a common factor, sort of in this case 2, and somehow I've sort of put a condition over here that's incompatible along that common factor. Okay, so there's not always, anyway, the point is there's not always a solution to such a pair of congruences. Like we might not always be able to find an x. Let's do a slightly more interesting one. So let's look at x congruent to 3 mod 8 and x congruent to 5 mod 9. And here I'm going to do it in a way that actually lets us systematically solve these things, building on some things we were doing earlier. So, okay. Well, I could just list out all the numbers. So I can look at 8 times 9, 72. So I know if I sort of change something by 72, I'm not going to change it mod 8 or mod 9. So I could just list all the numbers between 0 and 72 and compute a mod 8 and compute a mod 9 and sort of see which one gives me a solution, if one gives me a solution at all. And that would be one way to solve it. But that's going to take more room than I have on my computer screen. So let me do it a little bit more systematic way. Well, so let me start with this equation. So x is congruent to 3 mod 8. Well, this is just the same as saying x is equal to 3 plus 8 times y for some y. So there are lots of solutions to that. I mean, I could take x to be 3, I could take x to be 11, I could take x to be -5, and so on. I could plug in any value of y here. So good. So these give me all those solutions. So all the integers to satisfy this. But now I can take this and substitute it in over here. So then I get 3 plus 8y is congruent to 5 mod 9. So I get 8 times y is equal to 2 mod 9. And now I'm in the situation I was before, where I just have to solve this simple equation. So I need to sort of multiply by 1/8, but mod 9. So I need sort of to use that the multiplicative inverse of 8 is sort of in z mod 9z is actually 8 itself. So how you can see that is, well, 8 is congruent to -1 mod 9, and sort of -1 squared is 1. So -1 is its own inverse, so 8 is its own inverse. So, okay, so I just multiply both sides by 1/8, which mod 9 is 8. So I get sort of 8 times 8y is equal to 16 mod 9. And so you can check your math here to see where they got a multiplicative inverse. If I multiply this out, this is 64. And 64 is 63 plus 1. So this is, 64 is really congruent to 1 mod 9. So this is just using y is equal to, and then 16 mod 9. And let me even simplify that more. 16 mod 9 is the same as 7 mod 9. So y is congruent to 7 mod 9. Okay, and so now I can just choose any element that's congruent to 7 mod 9. So I could take y to be 7. Then I substitute back in for x. And I get x is equal to 3 plus 8 times 7. So 3 plus 8 times 7, so 3 plus 56, which is 59. And you can go back and, okay, if I look at 59 mod 8, the closest multiple of 8 is 56. So good, this is 3 mod 8. And if I look at 59 mod 9, the closest multiple of 9, I guess, is so now 54. Good. And so 54 plus 5 is 59. So you are 5 mod 9. Good. So this checks out. Okay, so this is how you can solve such a thing. And the only trick is that it's not always going to be so, and just like before, you're not always going to immediately see what the multiplicative inverse of the number that shows up here is. So sometimes you might have to use this Euclidean algorithm to compute it. Okay. And what we've really, and because we've given this systematic way to solve this equation, though, we've actually really sort of done a little bit more. We haven't just sort of told you how to solve such an equation, but we've shown you always can. I mean, if you think about it, like, this really shows that as long as the GCD, so as long as the GCD of these two numbers is 1, you're able to solve it. Because the key thing is, like, whatever this number was, like this 8, we had to sort of be able to invert it. So we had to be able to solve 8 times y is equal to something. So we had to sort of find 1/8 in z mod 9z. And so we need to know that 8 had a multiplicative inverse, but we've already seen that's the same as saying the GCD of 8 and 9 is 1. Like if the GCD, or sorry, the GCD of 8 and 9 is 1. Okay, so then, okay, so that's good. So it doesn't matter if this was 8 and 9. This would have worked anytime we had sort of some m and n where the GCD was 1. Okay, and that's what the Chinese remainder theorem says. So let me state a first version of it. We're going to go back in the future and maybe next week and give a different version, a little bit stronger version of the Chinese remainder theorem. But I'll just state this version that we've basically just established. It says if m and n are coprime, which means the GCD is 1, then for any a in z mod mz and b in z mod nz, you can find an integer x such that x is congruent to a mod m and x is congruent to b mod. This is supposed to say n. Okay, so that's what we sort of just argued. And moreover, like if you just trace through that argument we made and trace through that example we did, you see how to find, like what to do to find that solution. So it's not just that there exists a solution, but you really have a way to find a solution. Okay, and then if you sort of think back more to what we were doing up here, where we saw like this table is repeating every 6, or when we were saying sort of all where were we doing this? I mean, so okay, at some point I was talking about how, right, I could take x equals 5, but I could also sort of replace that with a multiple of, like if I added a multiple of 6, I'd still got a different solution. So here, that 6 was coming from 3 times 2. And the same thing is true in general. So not only can, if the GCD is, so if the GCD is 1, you can always solve such a congruence. You can always find an integer x that satisfies both these things. But moreover, sort of the x you find is going to be uniquely determined up to a multiple of m times n. So if you shift x by a multiple of m times n, like you don't change what it is mod m and you don't change what it is mod n. So somehow that's the most uniquely determined you possibly could be. And if you think about it a little bit, you'll see that really like that is exactly how uniquely determined you are. Okay, good. So we'll stop here and we'll talk about some related things in class on Thursday. See you there.